Oh, I got you. Okay. Promote to panelist. Okay. And I'm just going to make you a co-host because that'll make it really easy to share. And Casey, you can start letting people in because this is what they're going to see. And okay. So here's unless your board will I'm gonna get some water and we're gonna start in like a minute or so.
Yeah.
All right. Nope. We're gonna do it all from this podium here. All right. Thank you all so much for being here online and in person. I'm going to take this off, and all the presenters, when you get up here, you can take it off. For those of you who are coming back onto the island, all of you need to keep your masks on. Thank you very much. For those of you coming back to the island, welcome back. And for those of you who this is your first time, welcome. We're really happy to have all of you here today. My name is Jennifer Seavey. I'm the executive director of Shoals Marine Lab, and this is one of our favorite events every summer that we do, and you're going to see why. Shoals is a joint institution of the University of New Hampshire and Cornell. This is its 56th year of operation, and we are the largest and the oldest undergraduate focused marine lab in the country. Our strangely not no. Sorry, technical difficulties. There we go. Our mission is to provide outstanding experiential place-based education and to support innovative research programs focused on understanding and sustaining the marine environment. We facilitate discovery, learning, engagement among our students, the faculty, the researchers, and the public, all of which are aimed at enhancing the lives of our students, our community, and way beyond this island. For those of you who did not come out on the boat and are uncertain about where we are on Appledore Island. It's the largest of the Isles of Shoals, which is offshore of Portsmouth, New Hampshire. We just came 10 miles on the boat, and we're on about 100-acre island out here. There is no connection between the mainland and this island in terms of any facilities, and you're about to understand all of that very clearly, what that means to us. Sustainability out here is a real integrated part of our mission. We really work the phrase necessity as a mother of invention out here on this island. And over the last decade or so, we have built green infrastructure and a sustainability ethic that includes power generation, water conservation, waste treatment, food sourcing, and how we operate here. We care about this because we want to be excellent stewards of this, our island classroom and our laboratory space. The reason why we're here is the reason why we want to protect it. We want to create an outstanding and useful model for application back on the mainland or to other islands. We are dedicated to providing undergraduate education opportunities to further the development of sustainability. Amazingly, and one of the motivating factors maybe in the early years was there's a lot of cost savings about being sustainable, and we can put that cost savings back into our mission. And we're really grateful for the platform that our sustainability infrastructure provides to engage all of you. And I have some slides that show the success of our program over decades. So this is a graph of our diesel use in the blue line over from 2007 to a couple years ago. And over the last decade, we have reduced diesel use on this island 90%. And for me, personally, when I look at this graph and I look on the right where it says the percentage of that graph that's described by the results of conservation, that is a big take-home message off this island. Over 50% of our reduction in diesel use is because of conserving power in the first place. Energy Star appliances, all the ways that we operate here that help us not use the power in the first place. And then of course, building on top of that, our green infrastructure, which you can see in the little bit less than half reason why we've reduced our diesel over 90%. Another evidence of our success in May 2021, University of New Hampshire gave Shoals a Platinum Sustainability Award specifically for this internship program, something that we're incredibly proud of having built over the last decade. Also, we in 2020 received a really amazing grant from the U.S. Economic Development Administration with a team of University of New Hampshire engineers and social scientists to help conduct work in collaboration with external industry partners and nonprofit organizations to find viable solutions to energy and freshwater insecurity for islanded communities. That could be another island in the region or an isolated community on the mainland. So Shoals is really proud to be a part of this, providing a model system for this whole team to find ways to bring this off the island. This internship has been going since 2006. We have about 70 students who have run through this program over that time period. They are typically rising juniors and seniors. They do a number of things for the lab. They really act as consultants to us. They address our real world concerns out here, help us iterate our sustainability program and infrastructure over time. And one thing that I love about this program is that these students are building on all the things that other students did before them. So what an amazing way to do teamwork over time and help the lab really progress and build these model systems. None of this would be possible without a lot of people who are in this room right now that have helped build this program since 2006. Amazing number of people who have stayed with us the entire time. And Mike Dalton, who used to be the CEO of Unitil, was a really important founder of this organization. And Tom Johnson and Al Hansen, also in the room, have really helped push it forward from those early days. And Shoals staff have really carried this program. I really want to give a huge shout out to Ross and Mike Rosen, who have carried this over time, and a bunch of other Shoals staff, especially always the engineering staff have to always help a lot. this year, Dwayne and Ben. And then our communications intern gets support from our communications folks. Amy and Casey are here in the room. Tom Johnson, as I said, has been a longtime mentor, started as a Shoals staff and now has become a mentor to this program, has really helped the lab innovate over time. Martin Walsnick, who is in here somewhere, and Wei Wei Mo from the University of New Hampshire have also been incredibly instrumental in mentoring students and helping us progress forward. I love this. Jacob Shackman, who is working in the engineering field at Wright and Pierce Engineering. He was an SEI intern himself, and he actually came back to help the interns mentor them this year on an erosion project, which is a new direction for us and pretty amazing that the SEI students, the former interns, are now mentoring the current interns, which is awesome. And then all the people at Unitil who help us. Greg Walsh is here today and help with both mentoring the communications intern and the engineering internship. This internship is specifically sponsored by Unitil because they understand that what we're doing here has real world implications, and they get that, and we appreciate that they understand that, and we appreciate their support. So my last slide is just to introduce you to these amazing interns before Tom Johnson is going to come up and kind of talk about the whole program and how we got here. So going around this sort of rainbow from the left to the right is Zach Katz. He's from Cornell. Zach, maybe you should raise your hand over there too. Tamara Camus, also from Cornell, who I just want to shout out is the lone communications intern in a sea of engineers. So we appreciate her efforts to communicate the story. Jason Shao, also from Cornell. Tess Hayes from Tufts, and then Izzy Medeiros from the University of New Hampshire. So we are excited to hear from you all today, and I'm going to pass this over to Tom. We can bring up that computer so we can keep going. Stick with us while we switch. Is that one going to work for you?
Hello, hello. Okay, Tom, I think you're ready.
Thank you, Jen, for providing the introduction. As Jen mentioned, I'm Tom Johnson. I started here as a boat operator in the early 70s. It's been quite a while. More recently, I've come back as a mentor for the engineering program. And I want to give you a little bit of history on how the program started and what we've been doing over the last 16, 17 years. All right. What do I have to do to drive here? There we go. Now how do I get rid of that banner? Up. Okay. So the this internship started as a series of engineering workshop weekends in the 2003-2004 timeframe. And out of the 3 or 4 sessions, there was a sort of a laundry list of opportunities on the island to look at engineering aspects, which was far different from the marine sciences, which was the focus on the island. So what was happening and what we identified back then was, as the island grew, as we had more people, we had to put more systems in, and there wasn't any design that was going into it. We put in a bigger pump. The bigger pump, when we had to put in needed more power, we put in a bigger generator, and it's kind of spiraled and cycled for many years prior to that. And we recognized that in the early 2000s and started thinking about how do we start weaning the island away from diesel generated electric, which was the driver. Tilting it back so you can see me. There we go. So in 2005, so these were 2003, 2004, this was happening. In 2005, we proposed, so Mike Dalton and I proposed and Ross and others, but we proposed an internship, running this as an internship, a sustainability internship. And the director at the time, Willie Demas, said, go for it, which was great, and pretty much gave us free rein to design, figure out what we wanted to do. And we came up with a concept for the internship, talked about how we were going to run it, how we were going to figure out the tasking, how much work, how many students, worked through all that logistics. And then in the spring of 2006, sent out applications for interns and started the program in 2006. There we go. So the first internships, 2006, as Jen mentioned, I think the actual number was 65 engineering interns and 3 sustainability interns, so close to the 70 that have been run through the program here. We've had from 4 to 6 interns. We started with 4. We said, this is great. We went to 6. And then all of a sudden, that was a big workload for us as mentors and figuring out tasking. It was a lot of work. So we said, well, let's go to 5. And 5 is kind of an odd number because it just didn't work well for pairing up with tasks or the interns. So we went back to 4, and we've been at 4 ever since. And 4 has really worked well. We pull from across the country. I think we've typically had at least 1 Cornell and 1 UNH student. I'm not sure whether we've done it every year, but pretty consistently we've had 1 from either of the institutions in the program, but we pull from across the country. We've had students, just about every institution, coast to coast, come through the program. But we have found that we needed to limit it to rising juniors, rising seniors. What we found was rising sophomores did not have enough of the intro 101 engineering courses, and we were not in a position to teach that here. We needed them to come in with a basic understanding, and that's all we were asking for. So we did start limiting it to rising juniors, rising seniors. Got a little. So over the years, we've had varying number of tasks based on the complexity that we've seen for the task. Some we've determined to be more time intensive, less time intensive. So I'd say anywhere between 5 and 8 tasks in any given year. When we're planning the tasks, we're always looking ahead. How do we get ahead of the issue? Do we have a water issue? Do we have a power issue? Do we have a wastewater issue? What can we do to get ahead and understand an issue so that we know how to change it and improve it? And ideally, we like to get a task where we can study something, implement a change over the off season, and have next year's students and next year's interns study it again so that we can quantify what type of change that it has made. We start planning for next year in the fall because a lot of the tasking that we've asked the interns to do is required instrumentation. And if we don't have a water meter on something, or we don't have a power meter, we have to get that in place prior to the interns to start. So there's a lot of lead time in terms of figuring out the tasking for the next year. And there's also a lot of overlap between disciplines out here, which is why this is a nice forum for being able to study these disciplines. So I like to say that we have 4 major infrastructure systems on the island: freshwater, saltwater, wastewater, and electrical. And it's easy to see that. How do I get rid of this one bar up here? It's perfect. Go away. Yeah, okay. So that, of course, if we pump water, we require electricity. If we pump water down a sink, we have to deal with the waste. We have a running saltwater system to keep all the marine specimens alive, support the research and marine activities that are going on here. So there's an interrelationship here. If we put in a bigger pump, pushing more water, we need more power. We're pumping more water, we have to deal with it in a wastewater system. So it's a real nice system to say that just by saying you need more water, bigger pump is not the answer, because it might have a detrimental effect on another system that's on the island. Along with the 4 infrastructure systems, I would say the majority of the tasks have been focused on these 4 activities in some form or another, because these are the big hitters in terms of the island infrastructure. But we've also had tasks related to systems that are not part of those 4 infrastructure. And the one I'm really happy about is the upper left, which is our dashboard. We've been struggling for years. When we started the program, we were going around with clipboards every hour, writing down values, because that was the only way that we could get information. And over the years, we've been pushing to get electronic recording, electronic instrumentation on all the systems that we're interested in. And right now we have a dashboard up and running. I've got an iPad here. I'll start the dashboard. You can send it around. You can go through there. You can see what we're doing real time in terms of our water usage, our power usage, and it's really good from a instrumentation value. And I actually use it. The COVID kind of messed up sort of these symposiums, but we went online in 2019, and I'll show you an updated chart from the one that Jen showed you. And I actually pulled the information from the dashboard. I could sit at home, go to the dashboard, pull the information, update the chart. In prior years, I've been chasing Ross and Mike around, so find me the piece of paper that this is written down on. So it's tremendous, but this has been a long time coming. The interns have been instrumental in telling us what do we want on that dashboard, what format do we want the dashboard, how accessible do we want the dashboard. We've had several taskings related to getting us into the 21st century. Lower left, we've got food. Food, trash, composting, recycling. We've had studies to look at. After the intern, they'll get a survey, ask them how they like the program. The least liked task in 16 years has been the trash. We had the interns spread out all the trash. We take the trash ashore once a week. We spread it out down and it says, sort through it, tell me what's in this. And as a result of that, we found that we were doing a poor job of getting the message across on what to recycle, what to compost, and then what has to go ashore now. So that was instrumental in us setting up a better composting, recycling, trash process here on the island, getting up signage. So we have a lot of transient. When I say transient, we have week-long classes. It's hard to educate a new class every time. So we've got a lot better of signage and information how to get this across. Direct result of some of the tasking from the intern program. The lower right, transportation. We do a lot of transportation here. Both boats, which seems really obvious, but on land. We have numerous vehicles on land. We've studied what's the right type of vehicle, what's the right propulsion for these vehicles. We've looked at the boats. We've looked at how many times we run the boats, what's the efficiency of the boats, what's the right type of boats. Again, intern projects from previous years. And even in here, if you look up at these acoustic panels on the ceiling, this was an intern task. This room was incredibly hard to have a conversation in before. It's got hard walls, hard floor, glass. Everything was hard in here and it was loud. You could not have a conversation at mealtime with a person across the seat from me because it was so loud. So we brought in an acoustics engineer, worked with the intern, came up with a recommendation for this square footage of acoustic panels. We implemented it and we studied it again the next year. So this is the type of thing we like to build off of years, direct result of the intern program. Here's the updated chart from what Jen showed a little bit earlier. This is normalized to 2007. Remember, we started the program 2006. 2007 was the first time that we really had something we could believe in terms of saying that we needed to capture this and record it over time. The green line, the upper green line is the island load, and it's a mix of, we have 3 electrical grids on the island. One that's in here, notice the main grid, which is the dashed line, which you can see the majority of our usage is on that main grid. We have some power that comes from a smaller grid, but was actually here when we started the program, which was our test bed in terms of understanding how to implement solar, which is that little bit of dash line between the difference between the dash line and the solid line. It contributes some, but it's been a very small. We grew over time. We learned a lot about how to implement solar. It became the baseline for us understanding how we wanted to add to the solar systems, change the grid. And then more recently, we have another grid, which is the difference in like the 2018 above the dash lines is, and this is a grid that we put in to manage one pump. We have the salt water for me out here is the life and blood of the island. If we don't have a running saltwater system, we don't have a marine lab. So we have a saltwater pump that runs 24/7. That one single pump consumes about a third of the island, is about a third of the island load. So that's an incredibly energy intensive pump. It runs all the time. It's hard to get rid of the load. We're pumping a lot of water to keep the marine specimens alive. So we put in a independent grid just to run that pump. So that's the series of green lines shows the kind of the trend of what's happening with the island load. But the blue line is the diesel usage normalized over the same time. And a couple of things I want to point out about this chart, because I've spent a lot of time. I look at this chart more than you. So starting from 2007 to 2010, you can see that the green and the blue lines are more or less following each other. So that was a result of we started thinking about conservation. What can we do? We can get rid of all the incandescent light bulbs on the island, replace them with compact fluorescents. We can figure out what are our old inefficient pumps, and is there a more efficient pump we can replace it with? How many refrigerators do we have on the island? I don't know what the count was, but it was pretty high. Let's get all the old dorm-sized refrigerators off the island. We turned off the hot water in the dorms. Students didn't notice, right? So these are the types of things that we're doing, but there's definitely a result of conservation. And the diesel usage was tracking pretty close to those efforts in conservation in 2010. About then, we put in new generators, replace the old generators. We have new fuel efficient generators, and you can see a dramatic decrease in the fuel consumption just as a result of replacing the generators in the 2011 timeframe. 2011 to 2013, again, the curves kind of match their shape. The trend is the same. We didn't have any significant reduction, just followed the reduction from the conservation side. And again, we were doing this over time. We kept looking at things, looking at new systems. As we got one system fixed, even the lights, we went from incandescent to compact fluorescence, and from there to LEDs. So we've done 2 cycles of technology improvements since we started the program, just on the lighting. But then in 2014 was when we brought in our bigger solar systems. And there again, you see the big reduction in the diesel usage, because this is when we put in our larger solar grids, we put in the batteries, we put in the energy conservation building, huge reduction. And then we've added to these systems over the couple of years. It's hard to pick out the exact things that are happening there, but because of the increased solar capacity that we've been incrementally adding, you can see the continued reduction in the diesel fuel usage. So there's a couple of takeaways that I look at this and makes me think about what's the direction that we're going in terms of how do we do this. So, and I look primarily, I'm looking at we've done a 90% reduction in the diesel fuel usage, but I'm also looking at the green curve. And if you kind of imagine a line starting about 2014 to the present, it's almost flat, which means, we have really leveled off in our ability to make the island more efficient. And all that really means is that we've got to look a little harder. I think there's still potential in there to drive that green line, that island load down, but it seems like we've kind of hit kind of a base load in that flattening of the curve there. If you just imagine a line through it, don't count 2020, but if you kind of draw a line through the rest. So that's the part that I'm thinking, all right, what can we do next? We've looked at an awful lot of the systems on this island. We've upgraded an awful lot on the island, but what can we do next? There's still room for improvement. Hard to say. This is what we think about in the fall. What can we do? And this is how we use the information that we've got. I want to say that all the information on here from 2019 to the present was all pulled off the dashboard, which was a great part about it. Anyway, the other takeaway that I get from this is that there's no one fix for sustainability. There's no single thing that you can go to. Everything on here was an incremental change over a long period of time, starting in 2006. We've been picking away at it, and now we can say, yeah, we've done a significant change, but I can't point to one thing. I can point to a couple things that were significant, but the overall trend is a result of lots and lots and lots of incremental changes, looking at every aspect of this island. So on to the symposium. We want this to be an interactive symposium. Ask questions, don't be bashful. All right, I'll get them to ask you questions. So our agenda is we're going to see 3 presentations here in the morning. gonna take a break for lunch, then we're gonna do a walking tour for the last two presentations down around the island. We'll be back here by 3 o'clock and we'll pick up on a communications presentation after that. So, and we'll have opportunities. So I do want this to be interactive. Got a question, don't understand something on the slide? Put your hand up. Let's have a conversation. Okay. All right, guys. Yep.
Hey, thank you to Jen and thank you to Tom for those wonderful introductions. We are going to introduce ourselves again. My name is Zachary Katz. I am a rising senior at Cornell University studying engineering physics. I'm really excited to share with everyone what we've been doing over the past 4 weeks, being on this island and seeing how interconnected all the sustainability systems are has been really amazing. And it's also been a really unique experience because of how isolated the systems are. So I'm able to fully understand from generation to use how everything has been put together.
Hi, I'm Izzy Medeiros. Hey, Mom. I'm a rising senior at UNH. I'm studying civil engineering. And I've had a great time these last 4 weeks, just getting my hands dirty, being out in the field, learning a lot about the engineering process, and just doing some good.
Hello, hello. My name is Jason Shao. I am studying environmental engineering, and I will be a senior in the fall at Cornell. I would say being here on the island has been really valuable for me. Getting to see again over time the improvements the island's made with the sustainability has been really amazing, and I wanted to have my own part in that, play a note in the symphony that is the sustainable engineering legacy here. So I'm just really grateful to have the opportunity to work here.
Hi, I'm Tess Hayes. I'm a rising junior at Tufts University and I'm studying chemical engineering. It really has been incredible just to say again what everyone else has been saying, to work on an island where sustainability is such a priority and to see this at such a large scale in this incredible community and how hard everyone works. And just this environment has been so cool. Like just the other day, like literally yesterday, we were sitting here practicing our presentations and like saw whales out the window, which was probably the coolest thing ever. But it's been really incredible to work with such amazing people who prioritize environmentalism.
Great. So we were assigned 5 projects for to work on throughout the 4 weeks we were here. And the first one I'd like to share with you, we call the power of wind. So if you look behind you, you can see our wonderful wind turbine spinning in the breeze. So this wind turbine is actually new. It was installed June 2021 after our prior turbine experienced an internal electrical failure. So our task was to understand, is this new wind turbine performing as expected? The manufacturer has some specifications about how it should be performing, and we have measurements of what energy it's been producing. So we want to understand if it's been performing as manufacturers say, if it's performing as well as it can be. And another aspect of that is that we have 2 meters reading the power output from the turbine, except sometimes these readings have not been in sync with each other. So we're also looking to try to understand how to display the most accurate data on our dashboard. So we're looking to determine what the discrepancy is and how we can correct for it. So the 2021 interns, building on what their prior work did, had a couple of weeks with this new turbine while they were still here to understand a little bit about the meter discrepancy. This graph is showing the offset between the 2 meters compared to the current output on the that's being put on the dashboard. And they thought maybe this trend has something to do with wind speed. So they took a few data points and they made a trend line trying to determine what is the cause of this discrepancy. And you'll see that throughout our presentation, we've continued to work on that. Okay, so the first thing we wanted to do was to determine, is this turbine performing as expected? That takes a couple of things to understand. First, we need to understand the wind speed at hub height. Hub height is just the height to the center of the turbine blades. And then once we have an estimate of what this wind speed at hub height is, we can compare the theoretical which is the power that should be generating based on this wind speed, with the actual power generated based on the dashboard. And then, as I said before, we also want to understand the discrepancy between the meters measuring power and ensure that the data on our dashboard is displayed as accurately as possible. Hey, so this is a map of the Isles of Shoals, and an anemometer is something that measures the wind speed. So we had a couple anemometers around that we were using to get our wind measurements from. The first is on top of the radar tower. The Shoals has installed an anemometer there, and we measured the radar tower height to a height of 43 meters, and we use that measurement as one of our measurements to estimate the wind speed. We also there's a station operated by NOAA on White Island at a height of 32.3 meters above mean sea level that we have been getting wind data from. And here's the wind turbine, which is at a height of 36.4 meters. We use both the data points because although the radar tower is closer in terms of distance, it's actually there's a larger height discrepancy. So we want to understand how the wind speed typically increases with height in the lower atmosphere. So we want to understand how the different wind speeds are affected. So we want to use both the data. One question is, why not put an anemometer right on the wind turbine itself? And while that would be the most accurate data, it's hard we'd have to erect a new structure. It's hard to put one on the actual turbine because the turbine moves in the wind to determine how to best capture the most energy from the wind. So here is the dashboards going around on an iPad, but here's a screenshot of the dashboard. This is the wind page of the dashboard. We're showing the wind at White Island in white on this graph and the wind speed at the radar tower in yellow. The most important thing, I think, the most interesting thing about this graph is that the white speed is typically above the yellow line, and we'll quantify that later. But it's interesting because if you remember back to the prior slide, the white station was lower and wind speeds typically increase with height. We would expect it naturally to be the other way around. Possible explanation for this may be that the White Island is more isolated. Here on Appledore, the radar tower, there's buildings and trees around, while the White Island is more a rocky outcrop, more towards the open ocean. The other thing on this graph is the power generated. So this is the power that's being generated by calculated by one of the meters and displayed on the dashboard. And you can see there's a general trend that the power increases as the wind speed would increase and the blades are able to turn faster on the turbine. All right, but this data only shows the wind turbine, the wind speed at the height of the anemometer on White Island and the wind speed at the radar tower at the height of the radar tower. We want to understand what the wind speed is at the turbine itself. So in order to do that, we need to do some math. So this is a correction to hub height. There's two formulas we use. The top one is called a power law, because it's raised to a power, in this case, alpha. And the bottom one's called a log law because there's natural logarithms. Power law is typically used for heights of 20 meters and above in the atmosphere. And the log law is typically used for heights of 0 to 100 meters. And if you remember, our wind turbine's at 36.4 meters. So it's right in the middle. So we had to figure out which law is going to be the best for us to understand the wind speed. So the power law says that the wind speed at the height Z that we don't know, the wind turbine height, is equal to the wind speed at ZR, a reference height, in this case, either White Island or the radar tower, times the height that we want to know over the reference height raised to a power. Alpha traditionally has been 1/7, but we wanted to test a bunch of different values to see if there was a better fit. And the log law is very similar. It says the wind speed at this height Z the wind speed we don't know at the turbine height is equal to the wind speed at the height of the tower or the right island times the logarithm of Z, the height of the turbine over Z naught, which is something called a roughness length, and then over the height reference over the same roughness length. And this roughness length is shown in the table at the right. It's a qualitative factor that we choose based on what we think the terrain around is. So again, we chose a variety of Z naught values because this is a very unique terrain. We may think that there's many trees, hedges, and few buildings around here, but we're also on this isolated island surrounded by open ocean. So it's very complicated to figure out exactly what from one terrain description doesn't completely match what it is. Okay, so we took those values and we ran a bunch of different alpha values, a bunch of different roughness length values, and we determined that the best match we could find was an alpha value of 0.1. And it wasn't an exact match because, as I said, the wind speed at White Island was higher to begin with. So correcting it, you still had some discrepancy in the wind speed. And so this is a graph of our corrected wind speed. On the left side, we have the wind speed, and on the bottom right, we have 5 days in May of this year. In red, the corrected radar wind speed using this alpha value of 0.1, and in blue, the corrected wind speed shows that they're very similar in trend, but there are, of course, a few differences, and are set about to try to figure out and quantify what these differences were. So this is a normalized histogram. So I took each of the wind speeds averaged over an hour, and I using my correction for the radar tower and for White Island, I figured out what percentage of the wind speeds are between 3 and 4 meters per second, or 4 and 5 meters per second. And that's what's being shown on the left axis, what percentage of the wind speeds are at this value, and the Y, and on the x-axis, of course, the wind speed. And we plot it up as a histogram, and as expected, based on what we said about our observations of the dashboard graph, the radar wind speed is indeed on average a little bit slower. So the means are plotted as vertical lines. The radar wind speed mean is 6.25 meters per second. And the White Island wind speed is 6.55 meters per second. That's a 0.3 meter difference. Ideally, since the locations are quite close, we would like them to be the same. But as I said before, since the White Island is typically faster to begin with, 0.3 is very good. And then the also thing on this graph is called a Rayleigh power density function, or PDF. This is a typical profile of what the wind speed looks like in the atmosphere, in the lower atmosphere, and showing that our histogram fits the general trend of this. Is showing that we've come up with a reasonable result, a reasonable value of the wind speed. And to further that, we can also compare that to what other agencies have done for the wind speed. So this is the National Renewable Energy Lab, who publishes a chart showing across the United States. They call it the wind resource, but it's the wind speed at a specific height. This particular chart is showing the wind speed at 40 meters above the ground. It's a lot. There's a lot going on in this chart, but if we zoom into the Northeast, the Gulf of Maine, we can see that the wind speed they've put at 40 meters per second for right off the coast of Maine is 7 to 7.9 meters per second. If you remember, we said our average wind speed was 6.2, 6.3, 6.5. So it is a little bit lower, but there's a couple of reasons why that makes sense. This is for 40 meters and our wind turbine height is 36.4. So it's going to be a little bit lower, a little bit less wind speed. And we're on an island, not that far off the coast. So possibly something to do with the topography. It's not open ocean here. Yes, Russ?
Based on a year-round data?
Yes, this is based on year-round data. That's a great point. So we don't have year-round data. You'll hear that we take our blades off in the winter because we don't need as much power here on the island. So our data is just for usually the summer. And in the winter here, it's stormy, it's snowy. Would say there's typically higher wind speeds. So that's another reason that this may be a lower number. Yes. The histogram's over what since they installed the turbine, so about a year. Yeah, but it only has data for the summer part. So from when they took down the turbines in September to when they put it up in late March or early May, there was no data.
So your histogram is only for the summer.
No, I'm sorry. The histogram is for the full year. All right. So now that we have a wind speed that we can believe and we compare it to other things, now we have to understand how the power output relates to that wind speed. So on the left, we have the measured power output of the from the system, and on the right, we have the wind speed. This is the wind speed that that we have calculated based on the data from nearby anemometers. And we've time synced it. So at a particular wind speed, at a particular day, the power output was each of these red dots. The black line is from the manufacturer. So the turbine manufacturer, Berge, set out the turbine for 9 months, and they collected data on how fast that the turbine, at what wind speeds, they figured out what wind speeds the turbine, how much power it produced. So they produced this curve with their error bars of how much power they think that the wind turbine should produce based on their estimates. So the red dots are for the radar tower. And in this particular example, I've done an hour average. And they agree quite well. You'll see in the next slide, there's going to be 6 of these graphs for showing different things. So here we go. So the top row is all from White Island data. So this is all using the corrected wind speed, but starting with the White Island anemometer. And the bottom row is from the radar tower. And we've done a 10-minute average, hour average, and a 24-hour average. The first thing to notice is that as we continue to average over a longer and longer time period, the data becomes less scattered. It becomes closer to what the manufacturer has predicted, has experimentally shown that they think the turbine should produce. And the other thing to do is to compare between the radar tower data and the White Island data. So I think it's particularly clear in the middle column with the hour average that the White Island typically a little bit below what the estimated, what has been estimated by the manufacturer. Radar tower is pretty spot on, maybe a little bit above. And this makes perfect sense going back to the 0.3 meter per second discrepancy we saw in the histogram. It's that the White Island graph is just shifted a little bit to the right because all the wind speeds are a little bit faster. So overall, from this, we can understand that, especially if we average it over a long enough time period, that the wind turbine is performing as expected by the manufacturer. Next, let's take a little bit to look at how we're presenting that data to the dashboard.
Yes, as Zach has said, we are performing as we should, but now the important thing is how do we display that to the world? Here is a screenshot taken, these 2 meters are taken at the same time. Again, we have 2 meters. The one on the right is the VSC2. That is the one that comes with the turbine, and that is outputting data we believe to be the actual power output of the turbine. And then on the left, you have the AccuDC meter. Now this meter is where we get the data from to display on the dashboard. What we can see here is that these 2 data points do not coincide. The one on the right is a little bit less at 10.7 kilowatts, and the one on the left is 12.3 kilowatts. Here you have another instance. This time on the right, it says that the turbine is producing no power, while on the right, on the left, sorry, the AccuDC says that there's a little bit of a background of 0.08 kilowatts. And again, why is this important? Here, one of our biggest values is sustainability, and we want to make sure that we're displaying reliable and accurate data on this. One of the things here that you'll notice is that in both of these instances, the AccuDC is a little bit higher. And this is, again, something that the interns of last year noticed. Again, as Zach said before, they noticed that at higher power outputs, they noticed higher levels of discrepancy. But since the turbine was only here for a couple of weeks, they weren't able to get that much data. So we wanted to see ourselves whether higher wind speed also equaled higher offsets. But here's just first what we decided to do with the dashboard. On the orange line, you have the raw AccuDC data. On the bottom, you just have over time. And on the left axis, you have the power. And what they decided to do to show on the dashboard is to just shift it by 0.29 kilowatts. Again, as you saw, the AccuDC was generally higher, and they noticed at a different time period that they had saw an offset when there was no power generated, that the AccuDC put out an output of 0.29 kilowatts. So they decided across the board just to subtract it by 0.29 kilowatts. And that's what we display on the dashboard. But now that we've had time to gather more data, we thought maybe we could figure out a way to relate wind speed to that offset. We can say at this particular wind speed, we should adjust it by this much, as opposed to a flat constant value for every single wind speed. And here's what we found. There's a lot going on here, and I'll try to walk us through it. In the orange, which is correlated to the left axis, you have the power offset. This was measured by taking the AccuDC meter value and subtracting the VSC2 meter from that, again, which is the actual power output. On the right axis with purple, you have wind speed. And qualitatively, you can kind of see that the peaks in both sort of match up with each other. So maybe this idea that at higher wind speeds, you do have higher offsets, and we could come up with some relationship with how to adjust for that. Well, not exactly, because here on this graph, on the left axis, again, you see that offset, the AccuDC minus the VSC2. But on the bottom axis, this time we compared at each wind speed. And what you see here is that while yes, at higher wind speeds, you have a greater range of what the offset can be. So sometimes the offset can be up to 0.1, for instance. But these black dots, they also go down to 0. So again, while at higher wind speeds, you can have a bigger range, it doesn't necessarily mean you have an offset. You can still have the meters say the same thing at higher wind speeds. So in this case, it's not really easy to form a correlation between wind speed and the power offset between the two. So now we're sort of left with what to do with that. Well, what happens when you look at sort of the energy generation over time, right? These are values of instantaneous power. What in this instant are these turbines outputting? But again, what happens when you look over time? Well, here on the left axis, you have the cumulative energy generation over the week that we took data. In the middle line, the orange, you have the actual energy generation over the week, which came out to about 400 kilowatts. On the top, you have the AccuDC raw data without the offset. And as you can see, we're sort of the meter overestimates how much power we're generating, or how much energy we're generating. And then on the bottom gray line, you have basically what we're putting on the dashboard, what we're saying we're generating. And in this case, with the 0.29 offset, we're sort of underestimating how much energy we're generating over a period of time. And what this tells us is, well, we can look at the difference between the AccuDC without the offset and with the actual one and come up with our own offset to sort of match these data better. And here's what you see. With an offset of minus 0.13, you can see at the end of our week, the total energy generated is 400 kilowatts. And we think that this offset might be better because when you think about electricity, especially with your house, you're not really concerned about what's the power load of my house right now. You're concerned with how much energy did we use throughout the month. That's what your electricity bill is. And that's sort of the same idea here, is that at any given instant, the offset might not exactly show what the actual turbine is outputting, but at the end of a week, a month, or at the end of a season, we'll get a more accurate version of what we've generated over that time frame. I think that value is what's important here. So, oh, yes.
Yeah, I actually read that. Yeah. So this is from Way. So get ready, because it's multiple. And you might want to repeat because they can't hear me. Did you have a chance to check the R squared for each power output curve versus a Berkey graph? Which method conformed better, power law or log law? Which reference was the better estimate of the real wind speed for wave or the power? That was a lot of questions.
Yes, and I have it up here. Let's see. I think the first question is for me. Do you have a chance to check the R squared for each power output curve versus the Berkey graph? Oh, these are
all for me. This is from the 6 graph slide. So no, I did not have a chance to check the R squared. The power law and log law, we chose the power law, but based on, we were trying to minimize the discrepancy between the values of the mean wind speed. So if they were on top of each other, the 2 stations, we would expect them to have the same exact mean wind speed when we corrected to the turbine height. But since since wind speed typically increases with height, to get a reasonable estimate, we tried to minimize and found out this value of 0.3 was going to be the minimum that we got. They all disappeared. We don't know which one was. Yeah, okay, sorry. Yeah, which reference was the best estimator of the real wind speed, the White Island or the tower anemometer? And the answer to that is we don't know, because we don't have an anemometer at the wind turbine. We can backtrack based on the power output, but we haven't done a full analysis on that to understand exactly what the best estimate may be.
Let's see. But yes, to conclude, the turbine is performing as it should, which is great, but we weren't able to find a direct relationship between wind speed and power offset to sort of figure out some sort of formula to say, at this wind speed, you should offset it by this. But with our recommendation of a minus 0.13 kilowatt offset, at any given instant, it might not display the accurate power reading, but over a certain amount of time, the energy generation, which might be more indicative of how we're performing as an island, will be more accurate. And yes, that's our presentation on power of wind.
All right, thank you. Thank you all for that. Okay, that was a lot. I invite everybody to stand up and shake out for a second. Wow, that was sitting for a long time. Okay, that's enough standing. Sit back down. Strap in. We're still going strong here. Okay, raise your hand if this is your first time out here. This is y'all's first time out here too. Okay. All right, raise your hand if it's your second time out here. Okay, so we got some returners. That's awesome. Okay, let me ask another question. If you're from Maine or New Hampshire, can I get a woo woo? Okay, if you're from anywhere outside of New England, can I get a hey yeah? All right, that was pretty sweet. That was pretty sweet. Anybody interested in science in this room? Okay, what about engineering? What about art? Okay, that's what I'm talking about. All right, I think we're all warmed up now. We're ready to get back into it. So we have another project that focuses on the turbine back there. It's waving at us. And so for this project, we were tasked with designing a way to include the necessary amount of hydraulic fluid that's necessary for this turbine. So basically, every so often, this turbine gets tilted down for repairs, maintenance, or just when, like Zach said earlier, when the season's over and they don't want the turbine to suffer from any seasonal damage. But the problem is that when it is lowered, the hydraulic fluid that's necessary to kind of raise and lower the turbine leaks out, or sorry, it overflows out of the tank because there's not enough space for it. And so similarly, when it's raised back up, all this fluid needs to be added back in to the system. And this is, as it sounds, not incredibly efficient. And it takes a lot of time from the island staff that have their other jobs to do. So we were tasked with designing a modification to the existing system so that there would already be the necessary amount of fluid in this system to raise and lower the turbine.
All right, let's take a quick look at what a hydraulic system is, and then we'll understand how to incorporate it to our turbine's hydraulic system. So most basic hydraulic systems operate in a similar way. We have a reservoir of hydraulic fluid that's shown in the top in blue. And this hydraulic fluid, when the cylinder or piston, which is on the bottom, needs to be extended, when they need to get that power out, it's filtered and then it's pumped along this red line, the high pressure line, through a control valve and to the bottom of the piston, pushing the piston up, and this would be to raise the turbine up. Conversely, when they want to lower the turbine, the opposite happens. The control valve switches. So now the high pressure line is going into the top of the piston, and the piston is going to push back down, and the turbine will be lowered. However, these two operations take different amounts of fluid. So this is just a zoom in of what the piston looks like. When we want to raise the piston, the yellow fluids will expand and push the piston up. But when we want to lower the turbine, the blue will expand, pushing all that yellow fluid back into the reservoir. So this shows a basic idea of what hydraulics is trying to do. And now we'll take a look at what it looks like on the turbine.
Yes. So this is a schematic of two sides of the windmill out there. On the left, you see in the black kind of rectangle, that's the hydraulic cylinder. And above that is the piston rod. So that's what is doing the raising and lowering, or the mechanism, I suppose. And then there's the return line and the supply line. That's how the hydraulic fluid gets to the cylinder. And then they kind of snake down and around to the side. So that's what you see in the picture on the right. And those get sent to the pump, or yeah, I guess the pump is controlling what gets supplied and then when it's returned. And that box that's outlined in black is the existing tank. It's a little bit too small. Yeah, so this is like the same kind of thing. On the left, the tank is covered by that white tarp, but on the right, you can see the tank in its glory. And actually, if you can see this red gasket and these bolt holes on the side, pay attention to that. Keep that in the back of your mind. It's important for later.
Hey, so we have an idea of what the system's doing. Now we got to go out and measure it and figure out what the volume is in order to make our recommendation. So we went out to the turbine with our tape measures and our rulers, and we measured the piping, and we went online and found the schematics for the cylinder that was used, and we were able to estimate the volume of the cylinder plus all the piping up to the cylinder as 6.1 gallons. And then we took measurements of the existing tank to be 3.9 gallons. And then we assumed that when the cylinder is retracted, all that hydraulic fluid has to go back towards the reservoir to get overflow of 2.2 gallons, which is consistent with what the island engineers think when they have to bring out their buckets when they're lowering the turbine and there's overflow. And then we had to think about designing our new system. Typically in a hydraulic system, we want 20% tolerance over the amount of fluid we need, because as the system operates, the fluid heats up and expands, or maybe there's air in the fluid. So you just want a little bit of tolerance to ensure that there is no overflow. So in order to do that, we're gonna almost double the tank size. We're gonna add on 3.4 gallons to make the total tank size 7.3 gallons. And here are our proposed designs for that.
Yeah, so this is our first proposal. Everything that's outlined in light gray is existing. So in the dash red line, that's what we're proposing. So in this system, we'd have an additional tank kind of next to the existing tank connected with a U pipe, and that would maintain the level, the same level of the fluid in both of the tanks. And then on top of the proposed tank, there's a flange. So that would get drilled down into the tank and kind of has like a 90-degree angle wall that would get drilled into like a cantilever beam type thing. So it can be supported by the system or on the system. Okay, remember that gasket I told you to remember about? So that comes into play right here. In this proposal, we would remove that gasket and plate, and then we would put it kind of on the other side. And this new tank fits next to and into a little bit the existing tank, fits along the bolt hole patterns, and that would be attached in the same flange and beam method.
So off of these two recommendations, we recommend the second method, the removal of the plate, for two main reasons. First, it's easier to install and going to be easier to maintain. We have the flange right on the plate, and so we know exactly how big we need to make that tank in order to just attach it really easily instead of having to figure out how to connect the U pipe and how to drain it. And it's also going to be easier to maintain, because with that connection, it's really easy to open up again if we need to look in the inside of the tanks or clean out the tanks. In addition, because of that flange, we're going to have an elevated base of that second tank. So both the inlet and outlet pipes are existing in the first tank, and we want all the fluid to be able to flow towards them. So this will allow, since the second tank will be raised, for the fluid to flow nicely back towards the inlet pipe. Some takeaways from this project for me was to really understand a hydraulic system. They're ubiquitous around us, from airplanes to dump trucks. They're all around, and I really, coming into this, didn't have any idea how they work. So being able to understand and figure out how this windmill, this really heavy tower and windmill is tilted up for maintenance and repairs was really interesting.
Yeah, and I got a little taste of the magic of the iterative process. I made those CAD drawings and they don't seem like that impressive, I suppose, just by a first glance. But I had to change them what felt like 800 times. In fact, I finished my final design or my final edits to them yesterday. And I would kind of produce something and say, okay, I'm done, here it is. And then I'd get all this feedback and, adjust it and then say, okay, this time it's really done. And then, get feedback and adjust it. And so that was, it felt frustrating, but overall, I think it was, that's like the engineering process. Nothing's ever really done until it's done. And it's good I know that now rather than going into a career and, wanting to pull my hair out all the time. So that was really cool. And also in a lot of my classes, they kind of, I'm sure you guys all can relate to this. They tell us what needs to be done in order to solve the problem. And for this assignment, we really had to exercise our design knowledge between the two of us and make something new. And that was really interesting and really rewarding. Yes. Oh, yes. There in this in the first time we went out to the turbine, I think it was day one. Tom went to show us the tank and there's a lot of nesting gulls out there. And he unfortunately suffered the wrath of one gull that pooped on him. But thank goodness none of that happened to us. Maybe Tom just has that sparkle. But yeah, we worked around it. Honestly, I think it was best that we decided to wait a little bit to start this project so we could go out there and take measurements while the gulls were raising their babies and they got kind of a little bit older and they were a little less protective, but not by much. Yeah.
Did you explore opportunities for changing the hydraulic oil? And I know some people that will use reclaimed oil from a kitchen.
We didn't.
No.
We didn't explore that too much. No.
It's a good idea
That
that
is- yeah,
we're
that is
trying
a
to
really
look
good
into in the future.
We can mention that in our report to the future SEIs. Moving right along.
Hello, remember me? I'm back. So this is our third project. It is a drinking water life cycle analysis. So essentially we are looking at the freshwater system and the drinking water system on this island and just seeing essentially the processes of how it was brought here and what we expect of it. So in this life cycle analysis, we are evaluating sustainability of the system. In order to do that, we first have to know what sustainability is. For this system, we're looking at carbon emissions or carbon emission equivalents to evaluate the sustainability. And we're looking at the entire life cycle of the system. So we're not just looking at the system as it is here, we're looking at the manufacturing process, how that was, where it was manufactured, how it got here, transportation to Portsmouth, and then transportation from Portsmouth out here, like what kind of boats, how many trips did it need? We're also looking at maintenance. So I'm sure, as you all know, I'm pretty sure pipes are really important in all of our day-to-day lives, using like sinks, toilets, all that stuff. Those need to be replaced, and everyone I'm sure has talked to a plumber at some point. We can't just call a plumber here. So you have to look at when those pipes are replaced, how often they need to be replaced in that kind of process as well. And on top of that, what happens when the system is no longer needed or no longer usable? How is it disposed of? Is that disposal sustainable? Is it being recycled? Can we reuse parts or send them maybe to Star Island if they need those parts? Or is it just going to be put in a landfill? For this study, we did a 100-year system study. So I believe, as Jen mentioned earlier, the Marine Lab has been here for 56 years. That's only halfway there. And much of this system is very new. And the sustainability out here is immense and incredible. And we expect this Marine Lab to be here for a while. That is the whole point of this legacy and continuing to promote sustainability here. So we want that system to last for as long as possible and be maintained. So the 100-year system study is pretty applicable. And we're going to go into later in this presentation what the system looks like. So where the water comes from, how it travels throughout the island. Yeah, we'll hop right into it.
Yes, and the important thing to note is that life cycle assessment is very complex. Here is just one example. This is the process of getting cement. And you could see, of course, you have to get it from the quarry and the crusher and the transport. And then it goes through all this processing and then it gets us here. And you could see on one row, you can see the energy associated with each process for making a ton of cement. And then below that, you could see the carbon emissions associated with it. And you can imagine that this is just for one material in one component of our drinking water system here. So we have to find the numbers for each component and sort of have a total value of carbon, of kilograms of carbon equivalent at the end. Going into the drinking water or the freshwater system here, about every day we get about 1,000 gallons from the well on the reverse osmosis machine. These are used for things like cooking and drinking and laundry in the bathroom and all these different uses. The reverse osmosis machine specifically is run on excess power from the green grid. Here, again, we have the solar panels and we have the wind turbine, and these end up charging some batteries so that we don't have to use the diesel at night. But when the batteries are charged up and we have some excess power, what we do is we run this reverse osmosis machine. And what this does is takes the seawater and desalinates it so that we have some fresh water. And it's sort of almost like a battery because we have this excess power that would be wasted otherwise. So even though if we don't need fresh water at the time, we can sort of store the energy as fresh water and then use it as we need. And these are usually run when the forecast shows that it's going to be a sunny day. So we run it in the morning, and then throughout the day, we'll sometimes have, 150% of the island's demand being generated by our solar and our wind. So we can use some of that for the reverse osmosis. And this machine can easily produce over 1,000 gallons of water on a day that's run. On the bottom is a screenshot from the sustainability dashboard of our water usage. This is over a 24-hour period starting from noon and ending at noon. And what's interesting here is you can sort of pin out some patterns in there if you think about some of the goings-ons of the day. For example, there seems to be a little bit of a spike at around 1 p.m. that goes on. Here we have lunch at 12 p.m. or 12:30. So anyone want to wager a guess of what people are doing at right after lunch that would require a lot of water? Yeah. Washing dishes, exactly. And you could sort of see an interesting trend, a similar one. It's all the way on the right. You can see in the morning. You have a little bit before, we have breakfast at 7:30. So a little bit before, you can see a little bit of a spike. And then that might be people waking up. That might be people cooking. And then again, you can see it sort of drop. And that's sort of right when everyone's eating. No one's using water. Everyone's in here eating meal. And then again, you see it rise back up. So it's just interesting to see, you could sort of exactly pinpoint the island activity versus the water usage. And it's just sort of, you don't really think about it, but you can sort of see it in these dashboard. And now Izzy will show sort of the whole system itself.
Yeah, so I'll start with what I find to be the most interesting part. If this bar would go away, that's all right. So like Jason said, the reverse osmosis machine that we have makes salty, nasty seawater into potable water that we can drink and use to wash our dishes and take showers with. So there's a big pipe that sticks, I wish those seagulls would be quiet. There's a big pipe that sticks into the ocean, kind of where you came up. Yeah, there's like a little house type looking shed where you came off the dock. That holds the pump that pumps the seawater from the ocean into the reverse osmosis system. And once this water goes through the reverse osmosis system, it's then pumped to the cistern, which is a holding tank for all of our water that's potable. Similarly, we have a 20-foot deep freshwater well. So a lot of water gets pumped from there to the cistern as well. And this water that's in the cistern must be treated. So that's why we have chlorine. Chlorine comes in. There's a pump for the water from the well. There's a pump from the water from the RO to control how much chlorine is getting dosed to these two places. And once the water is from the cistern or in the cistern, it gets pumped to the pressure tank. And the pressure tank, if you turn around and see where the solar panels are on those like buildings down there, the pressure tank is around there. It's not exactly over there, but for landmark purposes. Yeah, it's huge. It's really cool. But the great thing about that is that all that water from down there has to come all the way up here. And so instead of using another pump and using all of that energy, the water is pressurized. And so it just gets sent here by physics, basically. And it gets sent to this very building that we're sitting in. And down below in the basement, there's a little control system. Then it gets sent out to all of the buildings that need it. Oops. Oh yeah. Okay. So to do this life cycle analysis, we use software called SimApro. And like the slide says, it considers all of the emissions for each object and material that we input into SimApro. So for example, we'll start with one piece of the drinking water system, which is the well. This isn't all the materials that went into making the well. This is just an example. So we decided that we needed 100 cubic feet of concrete. And based on measurements that we took and assumptions that we made. And so when we input this amount into SimApro, this amount of concrete, SimApro kind of does like the background work and says, okay, how much emissions goes into getting the aggregate to make concrete, the cement, the water. So it does, the four of us cannot imagine every single thing that needs to be input by every single piece of the system. And SimApro kind of does the background legwork of that when we say, we need concrete, we need tin, we need polypropylene. So following along the concrete, this row here. So once we put in all these inputs into SimApro spit out all of these CO2 equivalents over the lifetime of these materials that we're inputting. So for example, the concrete that we used, we assumed that it was just standard medium strength concrete here. And so by burning fossil fuels, it had 983 kilograms of carbon dioxide equivalent. And similarly, the biogenic column kind of describes how many kilograms of CO2 were produced, or equivalent kilograms would be produced by the concrete. And the biogenic really means that when organisms are breaking down the materials, they respirate just like we do, and they also produce carbon dioxide. So it's not as much as the fossil fuels. You can see in that entire column, the fossil fuels are really the heavy hitters when it comes to CO2 emissions, but it also affects microorganisms and land transformation. So similarly, like if land had to be disturbed to dig up materials, or if trees needed to be cut down for whatever reason, it would have had that impact, or that equivalent amount of CO2 emissions. So in total, 985.16 kilograms of CO2 equivalent would have been emitted over the lifetime of this concrete alone. So you can imagine how much goes into each little aspect of this entire drinking water system. And then we had to make a lot of assumptions. Like I said, we had to assume that this was, standard concrete. So we just kept track of our assumptions that we needed to make, because there were a lot, and you don't want that all up in here. You need it in a concrete place. So yeah. Yes.
On your previous slide, way asking online, on your schema, do you know where the discharge meters are located? If you can repeat that question.
Okay, Dr. Mo would like to know. Do we know where the discharge meters are located? I believe they're located in the shed that houses the cistern.
the well.
For the well.
There's the one, it's outside of it, but right by the cistern, behind the cistern, in line. And then for the RO, it's by the RO.
Okay, so Ross said that for the RO system, it's near the RO system, and for the well, it's near this information is near the cistern.
All right, so what Izzy just showed was just one tiny part of the spreadsheet. It was just free materials in the manufacturing process for making part of the well. We also had to think about the other parts of the system, the RO machine, the cistern, the pressure tank, and the distribution system. And we also had to think about the use phase. Does the RO need to have its filters and its oil changed? And then also the disposal phase. How are we getting these used up components off the island? And when something breaks down, maybe we saw that the concrete's gonna last 75 years. How do we get that off the island? How do we dispose of it? And combining all this information using SIMAPRO, we were able to come up with a total environmental impact. And this graph on the left is sorted by system component. On the left, we have kilograms of carbon dioxide equivalent on a logarithmic scale. And on the bottom, we have each of the contributions that Izzy just talked about, from fossil fuels, from biogenic, from land transportation, and the total emissions over this 100-year period. As you can see, fossil by a large margin is generally the highest equivalent on this left graph, in particular for the pressure tank and the well, and the biogenic and land transformation are smaller. And if we look at the total, the pressure tank is really highest because of it's made of stainless steel, and extraction of that steel and that whole entire process is a large component of the emissions. Same thing with the well. You saw all that tin that went into the well and the huge number on the prior slide for the amount of carbon dioxide equivalent emissions. Another interesting way to look at this is by life cycle stage instead of the system component. So we have the manufacturing of everything, we have the using it, and then we also have getting rid of it. This graph is interesting if we look at the total, because the manufacturing is the largest part. And since we did a 100-year study, if we increase the lifetime that the system is being used, because the use and maintenance is much lower than the manufacturing, it's going to become more sustainable because use and maintenance isn't using up as much, not releasing as much carbon dioxide as the manufacturing. Another way to look at this is by percentages. So this is the relative environmental impact study. So each of these bars goes up to 100%, even though we saw on the prior slide that fossil fuels is much, and by and large, the largest contributor. What's really interesting about the chart on the left is, again, by life cycle stage, is this biogenic component is mostly in the disposal. And that's because most of our waste goes to a landfill. As he was talking about, landfills use bacteria and other organisms in order to help break down, and that's what's releasing the biogenic carbon dioxide equivalent. Again, you can see in the total that the manufacturing assembly is upwards of 60, almost 70% of the system. So that is showing that the manufacturing is a large component, and that if we continue to use the system, it becomes more sustainable. If we look at the total column for the system component, we see that the pressure tank in purple, and because of the steel, and the well in blue because of the tin, are large components. And the reverse osmosis is that tiny bar in the bottom in blue is such a low because we try to run it only off of the green grid.
So if you're anything like me, the number was 3 million kilograms of CO2 equivalent released. I have no idea what that means. I have no way to conceptualize that. I can't even visualize 3 million of anything in my head. And that sounds pretty awful. 3 million kilograms, like to me, that's like just that number. If that number was handed to me, that sounds just not great. So it raises the question, is the system sustainable? And what does that 3 million kilograms look like? So a typical car will emit 404 grams of carbon dioxide per mile. And this is from the EPA. So that's about 0.4 kilograms per mile. To put that into perspective, that's almost 7.5 million miles. A lot of cars go kaput at like 200,000. So wow. That's the equivalent of driving around the world on the equator almost 300 times. And again, this probably is not helping your idea of sustainability. That, again, sounds horrible. And I understand that. So to put that into perspective and really show the sustainability of the system, we thought we would compare it to a method that used to be used. So on Star Island, they used to drive a ship into Portsmouth, fill up a 250-gallon tank of fresh water, and drive it back to the island 4 times a day to get their freshwater needs. We decided to analyze that for 100 years, see what that would produce for carbon dioxide equivalents. And you can see the imported water is in blue up here. That's almost double the carbon dioxide emissions than our system right now. And again, I believe, as Izzy and Zach mentioned earlier, the more you use this system, the more sustainable it, or specifically this system right here, the more you use it, the more sustainable it is. So the longer it runs for, the more use we get out of it and the better it becomes. So if we're here for 200 years, this graph is just going to get even, it's going to show even more how drastically, how much more sustainable this system is. So while that number does sound scary, I agree, really scary, it is significantly better than the other options that are available to run a lab like this on this island. So yeah, in conclusion, it is sustainable. And again, the value that this lab produces in research about marine life and educating students and encouraging people to go out there and continue to preserve marine life, act sustainably, that value is not even taken into account when looking at this, like this graph. So on top of it being sustainable, it is also encouraging sustainability practices across the world. So good job, Shoals. Yes, Jeff.
Question, if we just took this whole lab and pumped it over on the mainland, would this change the sustainability at all? There's lots of, institutions like this would be on a well in New Hampshire, and how might that differ from being on city water?
So that's a great question. I'm not entirely sure how to answer that. Realistically, I think you can look at how your city water is produced and how that system works versus your own well. So that might be a case-by-case basis, because you can look at all the materials. If you were digging your own well and putting all these materials into the ground, that might not be as sustainable as just hopping onto your city water grid. But if you have a well that's already there, like in the case here, this cistern that we use is actually one of the water tanks that was used for the hotel that used to be here. There used to be a hotel a long time ago that ended up burning down. And the cistern used to be where, I believe Rossi said, is where they used to keep like ice and like frozen things. So that we didn't just dig a hole in the ground and make a well. Like in this sustainability, that was already there, and it was something that was there that we decided to use. So in the case, Jen, of what you're saying, if you are in an area where there is a well, or, oh, you can use this that is already here that might have been used before, even if the materials used in that aren't quite sustainable, it is more sustainable to use what is already there than to dig your own well with like, oh, sustainable like use of like different materials there. So does that kind of answer your question, like case by case basis there?
And adding on to that, so the life cycle also considers, the life cycle considers transportation, like Jason, Tess, Zach have said. So, I mean, we need water out here. So a lot of things need to be boated over here. And if we were on the mainland, that wouldn't necessarily be the case. And also a lot of places might not need an RO system because when our well water is insufficient, like what do? We don't shower, we don't drink water. So we need that system, even though it has a lot of emissions associated with it, but we need it to survive out here. And I'm glad we have it because it's really, really cool how it works. And without it, we wouldn't be able to be here right now. Any other questions on this? On the chat or anything? Okay. Okay, so we have 2 more projects. We're not going to make you sit here for another hour and a half worth of presentations. We're just going to introduce these 2, and then we are going to, after lunch, pick them up on our field presentation. So Tess and I were in charge of the erosion control project here on the island. This has been my favorite project. I find it interesting. So Tess, please explain to me, I'm confused. What on Appledore is impacted by erosion?
Izzy, I'm so glad you asked. So I'm sure all of you walked here on a road. I'm hoping you didn't traverse the bushes. And I'm sure on the road that you notice, they're not paved. And we need to transport all of our food ourselves across the island. We can't just walk to a grocery store and bring back bags. We have to drive all of that food in tractors from the boat all the way here. If we had to carry that by hand, that would suck. So the roads are drastically impacted by erosion. And Izzy, could you tell me more about why that's so important?
Tess, erosion control is important for the very reason you just described. We use these roads to do a lot of stuff. And as you can see in this picture, this was from a couple years ago. A storm actually created all this storm water that took out the center of this road. And we still need to drive on these roads, Tess. So what are we going to do once all this water is gone and there's just this rutting created? Are we going to leave it like that? No way. We have to fill it in with fill. And so this fill you can also kind of see, and you'll be able to get a better image once we're out there. It's made of gravel, big gravel, but also fines. And so when this stormwater surges through, this fine material gets washed away. And so on a remote place like Appledore, it's really important that we think of design ways to mitigate erosion, because we need to keep, without proper methods in place, we need to keep replacing this fill. That costs money. That's a lot of work. And it's hard to get materials out here. So we need to protect these roads. But Tess, this seems like a lot of work, really difficult. How would we solve this problem?
It would be a lot of work. It's gonna be tough. We can't just call the paving company. That's not gonna work. So we're actually gonna show you some of our ideas and talk more about them this afternoon after lunch when we head out to the roads, and you guys will be able to see kind of our thought process, some of the methods that are currently in place, some of the problems that are really pressing that need to be addressed, and we're gonna talk to you about a couple of our ideas.
So get excited for that.
And then the other project we'll be showing you in the field is the rainwater collection for the Celia Thaxter Garden. Here on the island, we host this garden. It's preserved. Writer, poet Celia Thaxter used to live here, and she had her own garden here. We've done our best to try to preserve that. Some of the flowers that she kept, we can see through in her writing, and also some archaeological evidence. And of course, we need water and these plants need water. But the idea is that we can sort of use rainwater in order to water this, so that the demand isn't on our freshwater system. It's on we can collect rainwater and use that for the garden. And so the goal of our project was to see if we could even do that, if we can sustain the life of the garden using just rainwater through even dry spells in July. And how can we get this water to the garden with the system that we already have in place?
Jason mentioned dry spells in July. In the entire time we've been here for 4 weeks, it's rained 3 times. So our data collection on that front has been a challenge, but it has been a lot of fun. So to draw your attention here, I want to show you the collection tanks that are currently in place. So I want you to look at this picture here on the left-hand side. Those are the tanks where the water currently is. And a side note, that big silver tank to the left of those, that is the stainless steel tank that we were talking about before that required so much of the carbon emissions to get here for the water system. So we will actually see that in person. It is very large. But okay, so these are the collection tanks. These are both 800-gallon tanks, so a total of 1,600 gallons of water can be stored at a time. Half of those tanks are buried, and the water will run off that roof into the gutter system and into those tanks. From those tanks, it is pumped up to the garden. And if you guys want to turn around and look, you can see a bunch of people walking around where those blue umbrellas are. That is the garden. And the building that we're collecting rainwater off of is the really lopsided roof one over there, right next to the garden. The tanks sit on the right-hand side closer, and we'll show you when we're out there. That water is pumped up to the garden where there's a drip irrigation system. And this is an example of what Jen and Tom were talking about earlier, how we're building on other interns projects. The 2015 SEI interns did an analysis of the typical sprinkler system, and they decided that it would actually conserve water if they installed a drip irrigation system. So the 2016 interns then analyzed that drip irrigation system that was installed. And you can see it right here. Draw your attention to the middle photo. Right there, that hose that you can kind of see, that is the drip irrigation system. So it's hosing that runs throughout the entire garden. There are holes in the hosing and it waters underground, if that makes sense. So it drips water underneath. You're not spraying water up, and it said just feeds kind of right to the roots. And if you want to, again, all the way to the right, that is the general system. That is how the water flow works. Don't worry too much about it. We're going to show you guys more into that later. Yeah, so this is our 5th and final project. We wanted to, oh, yes, question, go.
Point out those tanks, I worked out here in 1999.
Yeah.
And those originally were for a sewage treatment plant.
Yeah.
So we stored them away somewhere. And
Mm-hmm.
when you think of what used to go into them, what they're doing now.
Yes. So to reiterate for the people on Zoom, we have a lovely guest here. He worked here in, you said, 1999?
99 to 2004.
99 to 2004, so 5 years. And the tanks that you see that are circled on your left-hand side of your screen, those white tanks were used as sewage tanks. And you can, again, this really goes along with the idea of Shoals recycling and being sustainable. And to add to that, thank you for bringing that up. The tanks that we are looking to install, we were proposed with like a variety of choices that are all reused. We're not browsing catalogs. We have tanks that have been donated by labs, I believe, that are no longer in use that we have taken to use, or we will be, after some, I guess, deductive reasoning, figuring out which ones we want, they will be brought out here to use for that water storage. So again, we're not just purchasing new tanks, we are reusing and recycling constantly, which is really, really cool to see. We wanted to give some thank yous. Thank you so much to Ross. Ross, make yourself known. Thank you, Ross. This would not be possible without you. Thank you for letting us do work under your living space. We appreciate it. A huge shout out to Tom. You guys saw him earlier. Tom showed us the island when we first got here, kind of facilitated conversation on the boat ride over, and eventually showed us where we got to live for these 4 weeks. Thank you for that. A huge shout out to Professor Wei Mo. Thank you for joining us online. Martin Wozniak, who's in the back here. Thank you, Martin, for all of your guidance. He is one of our mentors, primarily with the wind projects, and it has been so cool to see his expertise. John Durant, who's a professor at Tufts University, who I do not believe is here today, but thank you to him. He helped us with, might be online. John, if you're here, thank you so much. We appreciate you. He helped us with a lot of the water flow, really helped us look at stuff from a new angle that we hadn't considered before. Jacob Shackman, who Jen also mentioned earlier, he was an intern here in 2018. He actually came out to the island and walked us through some of the erosion and basically what he does for a living, which was really, really cool to see. Shout out to Tamara, who's right here. Tamara is our communications intern, and it's been so cool to see how you communicate what we're doing to all these wonderful people and everyone else. Thank you for working with us. It's been really cool to see how you work and how that happens.
We'd also like to give a big thank you to the island engineers, Ben Dufty and Dwayne Coey-Hain, otherwise known as Bean and Dwayne. They have been amazing resources, helped us think of some solutions to things, figure out how to use power tools, are always, around to help us, and we really appreciate that. Terry Cook, who is our garden steward, he's back there somewhere. He's awesome. Not only has he answered a lot of questions about Celia Thaxter's garden, but he's given us a lot of history about the island itself, the history of the garden, and has just been a really friendly face. So I've loved being around him. We all have loved working with him. Another big thank you to Dave Buck. Where is he? Oh, he's not here right now. And Mike Siegler. Mike, make yourself known. Thank you so much. They have also been around to help us out and offered their support and their critique. So we really appreciate that. Constructive criticism, we really appreciate that. And lastly, big thank you to the island staff, the kitchen staff, and the surge interns, because without the island staff, we wouldn't be here. Without the kitchen staff, we wouldn't be fed, and without the surge interns, we wouldn't have any fun. So thank you guys so much. Really appreciate it.
Okay, so a couple important things. For those of you online, please come back at 3 to hear tomorrow's presentation. That will be after lunch and after our field excursion. So please rejoin the Zoom call then. We'd love to see you back again. And for all of us here in this room, we are all going to exit this spot, and lunch is magically going to appear at 12:30. And then after lunch, woo, lunch, after lunch
Let's meet down at steps 115.
at 1:15. And
Steps outside these stone steps out here.
so bathroom break is a great time. If anyone wants to see the water conservation building, Tom will meet you down there and you can look at that. So lunch is back here at 12:30. Please leave this area just so they can have plenty of space to do all that. And thank you, those of you who joined us online. We hope to see you at 3.
If I could ask a little bit of help, move some chairs back along the tables. So we're ready for lunch. Grab a chair.
Let's see the chats.
Great job, guys. Perfect timing. You know, this is right on schedule. Good.
Thank you.
We got a nice work.
We got nice work from my way.
Thank you.
My mom said, "Wow, SEI team, impressive and inspiring." Thanks, Mom. Okay. Okay, bye-bye now.
Thank you so much for all your help.
Unmute and start video. I can't start video because host has stopped it. Can you start video? Jen? While you bear with tech with us for a moment, how has everybody's day at Shoals been?
Great.
One question that I was going to ask you at the end, but I'm going to ask you now instead to get video started on Zoom, is then have any of the sustainability solutions at Shoals really stuck out to you? Did anything catch your attention? Audience participation, super appreciated.
Water gardening.
Water garden?
Water gardening. Gardening water.
Yes.
The reverse osmosis. They're using.
Yeah, the reverse osmosis machine running on excess sustainable power is really cool. Anybody else? Things that caught people's eye today that they want to learn more about? Yeah, definitely. It's one of the things I've really loved about this internship has been building on the work of all these past years of interns. And that includes the people that were the ones to get through all of our stuff. And what else? Another question that I was going to ask you at the end, that I'm asking you now instead, reversing some systems here. Try to found easier or harder when you're having conversations about climate change or sustainability.
We got you now.
We're good? Okay. Hold on to that question. It's going to come at the end.
I don't know which screen you wanted me to share.
I
Come
got
back
it.
to that.
Thank you.
And your video is now on,
Perfect.
so you might want to stay on this side.
Wait, that's not here. There we go. All right. Thank you. Thank you, everybody that helped with that. I am short and also trying to be on Zoom at the same time. So I will be partially behind this podium and also looking out at you. So thank you, everybody, for bearing with me. This presentation is about sustainability at Shoals and beyond. Beyond meaning in all of your home communities that you go back to right after this. So we're going to keep things brief. My name is Tamara, and I am the communications intern. This is a photo of me. I'm a biology and society major at Cornell. I've got one semester left until I graduate. I'm minoring in science communication. One of the things that I think is really important to talk about when we talk about climate change work is what brings us to this work, because we all have different reasons that we end up in these jobs. For me, counterintuitively, the reason I'm interested in climate change is actually because I'm really interested in health. And as I've learned more about public health, I've learned just how much of our health is determined by the environment around us. We all rely on clean air, on clean water, on healthy food, and safe places to live. And climate change and environmental damage that increases the rate of natural disasters and extreme weather and that create pollution, that puts these things we rely on for our health at risk. But these problems are not inevitable and they can be mitigated. And that's what brought me to climate change work. It's actually my public health coursework. A few summers of work later, I applied to this position at Shoals Marine Lab to be the communications intern, profiling primarily the work done by all my lovely engineering friends you heard from today. And then this presentation will be focused on how you can take the sustainability ideas that you've learned here home with you. So, solar and wind energy. It has been improving really rapidly over the last decade. Let's see, technical, okay, just back up. So between 2011 and 2020, the use of solar and wind energy has quadrupled in the United States. And that happened largely because it's been getting cheaper and cheaper to build these energy setups. According to reporting by Popular Science, the cost of utility scale solar array dropped by about 90% during that decade. And similar, although not as dramatic, drop in the cost of utility scale wind energy. At the same time, sort of in parallel, it's become more and more possible for places like Shoals to make renewable energy like wind and solar our primary sources. So at this point, while we have diesel generators as backup in extreme circumstances, the vast majority of the electricity on this island comes from the solar and wind energy systems that you see. One of the reasons that it's been possible for solar and wind to get so much cheaper and then as a result get used in so many more places so fast is because sunlight and wind are both free. Unlike fossil fuel burning, electricity generation, you're not paying for raw materials. So the cost drops and usage expands as fast as the technology improves. Thanks to the hard work of engineers, including the future work of my colleagues here, it's going to be more and more possible to run electricity based on fossil fuels. This is based not on fossil fuels, but on renewable power. And the reason why that's so important is because fossil fuel burning is one of the major driving forces behind climate change. Everybody probably knows a lot about climate change, but just for a basic overview, when we burn fossil fuels, it releases greenhouse gases, and those function as a blanket in the atmosphere, trapping more of the sun's energy, turning up the thermostat on the world, and threatening to raise sea levels by melting glaciers. At the same time, one of the really important climate change threats in coastal communities like this is ocean acidification, because some of that excess carbon gets absorbed by the ocean. It lowers the pH of the ocean, and over time that puts marine resources and fish and all the people that rely on them at risk. So mitigating this by burning fewer fossil fuels and using more renewable energy is super important. And it's also super doable, and it's happening. So what could that look like, not just on Shoals where you can see it, but also in your own life? There are solar and wind options for everybody. There are different ways to get involved, but there are definitely options. One of them is residential solar panels. You may have seen houses with solar panels on the roofs. That installing residential solar panels is a really great option for a lot of people. It can lower your electric bills. Some people actually get to the point where they're feeding power into the grid. That might be possible depending on where you live. For a lot of people though, solar panel installation in your own home, whether because of location or whether because you're renting, it's not necessarily possible, but you can still get involved if you live in an area that uses or has access to community solar. Community solar is a larger array that you pay into, and then your electricity is coming from that solar array. And if neither of these options exist in your area, one of the really important ways that you can get involved is by being a voice in support of solar and wind farms. There's often some pushback and some community dialogue around new energy installations near a town, in a county, in a state. And your representatives really care about what kind of energy options you want to have. So if the government where you are is opening up a comment period and asking people, how do you feel about having some offshore wind? How do you feel about having a big solar array next door, a utility scale solar array? You can be one of the people saying, yes, I absolutely want that option. Because then if enough people do that, if enough people join you, then you could have easier options for buying green power from the grid. Water conservation. Here at Shoals, we build for our environment.
Just gonna minimize this, get this out of your way. Keep talking.
We build for our environment out here. Our environment for us is being surrounded by the ocean, as you probably felt in your long boat ride over. That means that while we have plenty of salt water around, fresh water is kind of at a premium. So we have a freshwater well on the island where we get the, excuse me. Okay. We have a freshwater well on the island where we get the majority of our fresh water, but we also keep a really close eye on the level in that well. Having slight technical difficulties with this presentation. It just doesn't like me very much. Give me 1 second. Okay. We're just gonna ignore that. Sorry. There was an arrow. Just gonna let it be. So, okay, it just has very delayed response time. The island Wi-Fi is great, but sometimes it doesn't like us very much. So we've got well water. That's where we get most of our water from, but we supplement that with reverse osmosis because we do not want to run down the well. Being really careful about groundwater conservation is important across the US and across the world because it can take a really long time to replenish underwater aquifers or underground aquifers, and we're trying not to do that. So we use the reverse osmosis machine, and as much as possible, we power that with excess renewable energy. That way, when there is a day when the well is running low and it's also still and it's cloudy out, we don't have to use the diesel generator. We can use the extra water produced by the reverse osmosis machine to supplement our water supply. We also, as you heard from the engineers earlier, use rainwater to provide water for the plants. The Coeliothexter's garden is a super important part of this island. And also, as we're conserving freshwater resources, we're not trying to overuse the well water or overuse this energy intensive reverse osmosis process. We're really trying to keep that water for people. And so, but also keep the plants alive. And that's where rainwater catchment and improvements come in. So my question for you is, do you know where your water comes from? Have you asked about or thought about where the water that comes out of your tap at home comes from where you live? Because it could be from a few different places. It could be from reservoirs. Maybe you're tied into a well in your home. But maybe your municipality is doing a great job of managing water resources based on what makes sense for the area, or maybe they're overdrawing from a resource that might be harder to replenish. And if that's the case, then you can, as you're going to hear me keep saying, you can be a voice for green change. You can make it known to your local representatives that you care, not only that you can get water from your tap now, but that you can sustainably get water from your tap 10, 20, 30 years from now. And if they know that enough people care about that, they might be more careful about where they draw from. We are, yep, great. So lifestyle changes are super helpful when it comes to water conservation. Here at Shoals, you may have heard, if you're the family or friends of people working here or learning here, that we take showers twice a week and we do laundry every 2 weeks. But that's because we're on an island and water supplies are a little extra limited. But even on the mainland, where you have less of a risk of running down the one well in the area, there are strategies you can try to conserve water. Those can look like short showers. Showers are one of the major ways in our day-to-day lives we use a lot of water, and you can get clean while just spending less time. Water saving appliances and practices are super important. So that could mean that the next time you're replacing a device like a toilet that uses water, you can get the low flow option or consider whether that is right for you. Water saving practices could mean every time you see a leak, making sure you get leaks fixed, because small leaks over time, you really can lose quite a bit of water. And if you are in an area where rainwater collection is a possibility, potentially to irrigate your garden, it's something to consider. Recycling and composting. If you really think about it, nature is constantly recycling. Plants grow, they die, they fertilize the next generation of plants in the process. If you compost, your leftovers could be food for flowers, like the ones you've seen here. Here at Shoals, we do quite a bit of recycling and composting as much as is possible. Recycling means that the materials that make the products you're using and can no longer use, those materials can become new products again instead of filling up a landfill. And so to keep your waste out of the landfill, one thing that you can consider that we've done here is signs. It can be really hard to keep track of just what can go into recycling versus compost versus the trash. And the last thing you want to do is contaminate compost or recycling that you're shipping out to somewhere, because then they can't use it. And then that all goes in the landfill. So it's better to throw a little less in the recycling if it means that you're only recycling what you actually can. And that's where signs like the ones we have here can be a simple but really effective tool for growing more flowers with your leftovers and making more new water bottles with your old ones and whatever else you can think of for composting and recycling materials. Finally, as we've been doing here, we just talked about sustainability and climate all day. Now we're going to talk about talking about sustainability and climate. It's very meta. The five of us have been doing climate communications, sustainability communications all day, and that has been my primary job out here. I've been writing articles after interviewing the engineering interns about their work. I've been making social media posts. You should follow Shoals on Facebook, Instagram, and Twitter. You can see all sorts of fun photos of life out here. But sustainability communications doesn't just look like the work that I do. We all communicate every day with the people that we know. Communications research, and also common sense, tells us something called the trusted messenger effect. People are more likely to believe information coming from somebody they're familiar with than coming from a stranger. That means that you can be a source for information and can be a source for persuasion in your communities. And you can actually be the best resource in your community. You can amplify correct information. You can make people feel empowered to fight climate change. You can be the source of green information where you are. But also, these conversations are really hard. Climate change is huge and overwhelming, and it has the possibility to affect so many different things. So I wanted to end today with a discussion with all of you about what you've learned on the island, and also about what climate conversations are like for you, what makes them easier, what makes them harder, and what you're thinking about telling people when you go back home. So also, before we do that, just a quick thank you to everybody I've been working with. I've learned so much working with and living alongside all the scientists and engineers and students on this island. Shout out to the island staff for keeping us all, fed and housed and living on this remote patch of rock covered in angry seabirds. I've loved my time out here. I've got 1 week to go, but it's been an incredible journey. So thank you. And now discussion time. So that question I asked at the beginning, that I would like to ask you all now is, have you had climate conversations in your own lives, in your own communities, and what makes them easier or harder?
I think one thing that was making climate conversations harder and harder is the terrifying news that we're getting every day, and all these headlines saying that we have X so many years to stop it and these detrimental things are happening. We have a lot of people lose hope
Yeah, I absolutely hear that. And I definitely feel that way sometimes because I read so much climate news for my work that it can be hard. But the way that I like to talk to people about it is this idea of harm reduction, that more people safe, more environment safer is good. Anything we can do to reduce the harm, to mitigate the problems is worth the work. So it takes it from this sort of all or nothing, we win or we lose, to how much better can we make this? And at least for me, I've found that's helped to make sure I don't get paralyzed. Anybody else? I also want to be mindful of boat time. Yes.
I think one of the things that makes it interesting to talk about climate change is that we're seeing so many effects like day to day that are like happening right in front of us. It's not like this hypothetical theoretical thing. We're definitely seeing the changes like in real time right before our eyes. So
Yeah, definitely. Anybody else? Hands. If not, yep.
So you said you're reading a lot of climate news.
Mhm.
Is what you read oftentimes having a positive spin, or is it more doom and gloom? I'm not sure what your sources are, but what do you think about? Because like I know what I personally think. I'm just wondering what your opinion is about the mood of messaging, because you can put a positive spin on this if you want to. You can.
Yeah. I think it's really important to be aware of climate problems, but some of the coverage that I find the most interesting is critical solutions coverage. So like Tom said, there's no one silver bullet, there's no one answer out of this, but there are a lot of really interesting options to mitigate different things that have pluses and that have minuses. So what I would encourage you, if you're looking to stay up to date on climate news, but also not become very sad, to look for critical solutions coverage that helps you judge what solutions are working or not, as well as the problems coverage. So look at the wildfire information, and then also how they're maybe working on controlled burns and how they're working or not, stuff like that. And yes.
I think challenging how what you do things in general sort of conversation because of how conversation.
Yeah.
But something really encouraging is to realize like how many people are involved. Climate change. We're talking about building the. I don't remember what it's called, like the net zero house. So it's like a house that is net zero carbon. And realize that there are a lot of people who have this as like a meaningful work and are really involved.
Absolutely. Meeting people doing climate change work has been a huge source of hope for me. I believe we're coming to time, but one thing I invite you all to think about is what makes you feel hopeful about the fight against climate change. And so what solutions really catch your attention and how you can share that and advocate for that in your communities. I can tell you that one thing that makes me feel hopeful is seeing audiences like you interested in learning about this work, because then we all have the potential to find ways in our own lives to build a healthier future for ourselves and for our environments. Thank you so much. I don't want to keep you from the boat, but thanks for coming out.
We would like to have all of the interns come on up.
Just gotta turn this off. There's a remote. There's a remote somewhere.
Oh,
Thank you.